So good afternoon, everyone. Today we have a pleasure to have a talk by Professor Bertrand Guenin. Bertrand obtained he was a graduate from EPFL at Lausanne, and he obtained a PhD degree from Carnegie Mellon under the supervision of Gerard Cornuejos, who is the second author. Then Bertrand had several postdoc positions, one in Georgia Tech and one at Fields Institute in Toronto. Bertrand is a recipient of several highly prestigious prizes, such as Fulkerson Prize, Tucker Prize, and Siam Outstanding Paper Prize. And another thing that I would like to mention, one of the other authors on of the results is Ahmed Abdi, who is a graduate from University of Waterloo and who did PhD under the supervision of Professor Guenin, and now is a professor at London School of Economics. Yeah.
All right, thank you for the kind introduction. So my talk is called Bridging the Gap Between Integer Programming and Linear Programming. And this turned off, apparently. There we go. All right, so whenever I teach integer programming in my introductory class on optimization, I tell the students to get an integer program, you start with a linear program, and then you add the restriction that some of the variables, or all of the variables, have to take integer values. Right? That's a simple-minded way of defining an integer program. And that raises the following question. Can you put other restrictions on the variable x? Right? So rather than saying that the variable have to take integer values, you're going to restrict the variables to have to take some value in a set L, right? So if I choose L to be the set of reals, I get linear programming. If I pick L to be the set of integers, I get integer programming. Can I pick something different and get something that is sort of meaningful? So there are some choices for L. So one choice is to look at the rationals where the denominators are powers of 2. Those are called dyadic rational, right? So pick a rational, the denominator is a power of 2. Those are nice numbers, they have nice properties. And so you could imagine that you're maximizing that function there, subject to some linear constraints, and you're restricting every variable to be one of those dyadic rational. Now, why stopping at powers of 2, right? You could say, well, I can pick any prime, and looking at rationals where the denominator is an arbitrary, I take an arbitrary prime, and the denominator is a power of that prime. And then you get what we call p-adic rational. So I look at all the rational where the denominator is a power of p. So if p is 2, I get two adic rationals, which are just dyadic rationals here. So that's another choice you could pick, restrict all your variables to be in that set. Or you could do something slightly more exotic. I could look at what we called bracket p-adic rationals. So there you look at rationals where the denominators is a product of powers of primes, where all the primes are between 2 and p. Okay, so those are a number of different choices. And you could say, well, what's the most sensible, most general choice for L that is still sensible? All right, so let's just try to think of that, right? So again, we're looking at this optimization problem here. And I want to restrict every variable to be in a set L. And I would like to pick the set L to be as general as I can, but so that I still get a sensible optimization problem. All right, so what do I need? Well, probably one thing I need is to make sure that L together with addition forms a group, because I certainly want to be able to do some computation with it. So that's going to be a requirement. There's another requirement which I'm going to need, is that L should be a dense subset of the reals. And why is that? So there's a result that says that if you have a subgroup of R and it is not dense, then the set L that you get is just a scaling of the integers, just at x times the integers. And then if you look at the corresponding optimization problem, it's just equivalent to integer programming. So you're not getting anything new. So we don't want to do that either, right? So our second requirement, if we don't want to get integer program, is that it should be dense. Now, I need something else, right? Because so far, I'm not even able to tell you whether some number is in L or not. So the easiest way of, the least restrictive way of doing this is to have a membership oracle, right? So I get a black box and I give it a number and it tells me, yes, it is in L, or no, it's not in L. All right, is that all I need? Well, I'm going to do computations, right? So if I do computations, I have to somehow represent those numbers on my computer. So I probably want to work with rational numbers. I mean, even my membership oracle is not really well defined, right? I give it a number. What do I give it? Well, I want to give it a rational number, and then the oracle is going to tell me it's in L or not in L. And so if I want to work with rational numbers, I need another restriction. And that restriction is going to be that L restricted to the rational is still dense in R. Right? So this is somehow stronger than the second condition, that L has to be dense. And let me explain why you need that. So there's a little result that will explain why you need this. So suppose I want to solve the feasibility problem, right? So I just look at AX smaller than or equal to B. I look at the polyhedron which is formed by that. And I want to know whether there's a point in Ln in here, right? So those are my feasible solution, right? And what the theorem here tells you is that it tells you that if you have this density condition, whenever you have a feasible solution, you also have a feasible solution that is rational. And if you want to work with rational numbers, you certainly need that. And if you don't have this condition, then you can construct an example where the only feasible solution that you have, right, are non-rational, and though you can't work with rational numbers. So you really need to have this condition here. All right, so those are the three conditions that you need, right? And
so what is so important about being able to have a rational? I mean, you divide LP to be over the reals.
Well, exactly. So I don't want to restrict. I could just say L is rational, right? But if I defined a linear program, I don't say, well, we have to restrict all my variables to be rational. You just say the variables are real, and then when we solve it, we just work with rational. So I want to have a setting which is, in the same spirit, right? So I'm allowing you to have non-rational number as part of L, but then I need to have sufficiently many rationals so that I can actually do the computation over the rational.
For LP, you said it was over the real, so you were accepting real answers to LP.
Yeah, but the rational number is a dense subset of R, right? So I have the same property. So if L is R, right, then I have R intersection Q is dense in R, right? So it's the same condition. The third condition is the same condition there.
And your first condition, doesn't that exclude, say, the LP, all the floating point representable numbers on a computer? Because you add those two together, you might not get floating point representable numbers.
Yeah, so you need to make sure that it's closed under addition. Otherwise, we can't do anything. Yeah, so that's our condition to make it work. All right, so I'm going to replace the third condition here by just saying that we're going to require that L contains all p-adic rationals. So I'm going to make sure that my set L contains all of the rational where the denominators are powers of p for a particular choice of p. Right? And now I've decided what my set L is. It's somehow almost the most general. I've just weakened my foot condition a little bit by picking an explicit dense subset of rational inside L. And now I claim that once you do this, you have a problem that can be solved in oracle polynomial time. Now, why is it oracle polynomial time? Well, because I got a membership oracle, right? And so it's a black box. So if I choose specific choices for L, so for instance, I choose L to be the dyadic number, then I don't need an oracle because I can just check whether a number is dyadic or not, right? So oracle polynomial in that case would just become polynomial, right? So in particular, it tells you that I can solve this where X is dyadic, or X is p-adic, or X is bracket p-adic for the definition I gave before. All right, so that's the first result I want to discuss a little bit, but I have to be a little more clear about what I mean by actually solving it, given this class of problem. So trivially, right, if I look at this optimization problem, I'm going to have one of four outcomes, right? It could be infeasible, could be unbounded, it could have an optimal solution, or I can have the fourth box where it could be anything else, which is not in the first three boxes, right? And so I need to tell you what I do when I get into each of those boxes there. And I want to point out that, unlike linear programming, the fourth box is non-empty. So if I look here at a very simple problem, I just have a single variable, and I have a single constraint that says 3x is smaller than or equal to 1. I'm trying to make x as large as possible. And I'm restricting x to be dyadic, so rational denominator is powers of 2, right? There is no optimal solution, right? And so I may actually end up in that fourth box here. All right, so what do we do? So the algorithm is going to, well, it's going to return certificates if you are in each of those four cases to certify that you actually are in those cases. And then if you are in the fourth case, it's actually going to do something more. You can show that, in fact, the supremum here is actually going to be equal to its LP relaxation. So if I remove the LP relaxation, it's just I remove the restriction that x should be in ln. And then the supremum is actually going to be equal to the LP relaxation. And then if you give me any epsilon as part of the input, then I can just get an epsilon approximation, right? So I can get as close approximation as I want if I'm in a fourth outcome. All right, so that's what we mean by solving it. All right, so I want to give you a little bit an idea of what goes into the proof. So I want to go back to standard results about integer programming and how to extend them, right? So here's a decision problem. I take a system of linear equation. I tell you that my variable should be integer. I want to decide whether there's a solution to that, right? So an integer solution to a system of linear equation. Is that hard? Some people took my IP class. It's in P, right? You can solve that. And in fact, there's a nice theorem of the alternative for that. And let me just sort of state it, right? It just says that there's only one reason you wouldn't have a solution to ax equal to b, x being integer. It happens if you can take a linear combination of the constraints so that on the left-hand side, you get an integer vector, and on the right-hand side, you get something that is not integer. All right, so this is what happens for integers. So what if I'm trying to look at what happens for L, right? So I pick L that is a subgroup of R+, and I want to do almost the same thing. I want to find ax equal to b, but now I'm restricting x to ln. And I claim that essentially the same result holds, right? So you get a linear combination of the constraint. Left-hand side is still integer, but the right-hand side now is not in L. Right? So let me argue the easy direction, but you've probably worked it out. Right? So suppose for a contradiction you had a solution to Ax equal to B, and then you had y as in 2, right? Then what you do is you take your equation Ax equal to B and you left multiply by y transpose, right? And you just look at that equation. So y transpose A, that's just an integer vector, and x is in Ln. So if I have something which is in L, and I multiply by some integer, it's still going to be in L, because I have this, it forms a group, so it's closed on addition. So the left-hand side is just going to give me some number which is going to be in L, but I'm telling you that the right-hand side is not in L, so you get a contradiction. Right? So this is the easy direction. It works exactly the same way as you do it for integers. And what about the other direction? It's the same proof. So if you ever seen the proof for integers, you just squint at it, and it just goes through exactly the same way. Right? So I'm not going to do that part there. Just write it down in Hermite normal form. But the nice thing about this proof is also that it gives you an algorithm. So it gives you a way of actually checking whether you have such a solution or no solution. OK, so this is one ingredient, just a straightforward extension of results about integers. Now let's look at this decision problem. So do I have an integer point in a polyhedron? Well, that's, of course, NP complete, right? And if I look at the analog that we have there, for instance, I say x is dyadic in a polyhedron. Is it empty? Well, this is in P, right? In fact, it's in P for any of the choice of L which I picked. So for instance, if you wanted to know, if you have a polyhedron, whether there's a rational point in it where the denominator is a power of 23. 23 is prime, right? Then you could do that in polynomial time. So what makes it work is that the set L is a dense set. This is really where the magic happens. That's a big difference between integer programming. And let me give you a lemma that tells you why it matters that you have a dense set. All right, so here's a key result. So my assumption is simply that L plus is a subgroup of R plus, and that L is a dense subset of R. Right? That's the only thing I'm using for assumption. And now I give you a rational polyhedron, and I tell you to check if there's a point in Ln that is in my polyhedron. All I need to do is to look at its affine hull and check if there's a point in Ln. Right? So if there's a point, right, in a polyhedron and in Ln, it's also in a affine hull, right? But the other direction is the thing that's surprising. It's really not true for integer programs. And you can see why it makes things easier, because checking if a point is in a affine hull is sort of easy, right? Because it's just looking at a system of linear constraints and see whether you have a solution where x is in Ln, right? So this is really where the magic happens. And I'm not going to get really into the proof, but let me just sort of point out why this is true, very briefly. So what happens is that as soon as you get one point which is in that affine hull, because that affine hull is a rational affine space, that comes from the fact that this is a rational polyhedron, right? So in other words, it's an affine space that is described by, an integer matrix and an integer vector. As soon as you get one point which is in L, then in fact you get a dense subset in that affine space, which is going to be in Ln is going to be dense in that affine subspace. And so you do the obvious afterwards. You just go into your polyhedron and you just pick some point which is in the relative interior of your polyhedron there. And then you just say, well, my affine hull is a dense subset, so there's some point which is close to it, which is still in your affine hull, right? But then it's still going to be in P, in S, in your polyhedron, right? And in fact, you can just look at how this is done computationally, and you can easily turn that into a procedure in algorithm. So it's a fairly simple idea, but it's actually very powerful for all of the results I'll mention. So I don't want to describe all of the procedures, all of the steps for the algorithm. So let me just discuss a little bit about feasibility, right? So we will look at a polyhedron S, which is given by a system of integer constraints, ax smaller than or equal to b. And I want to know whether there's a point x bar, which is in that polyhedron and in Ln, right, where we have the assumption that we discussed earlier. Right, so how does the algorithm work? Well, the first thing you do is you want to identify the affine hull of the polyhedron. You can just use linear programming to do that. In fact, you can just run a single linear program where you just look for a strictly complementary pairs, and it actually give you all the implicit equality which define the affine hull. So just run LP just once. And then, well, then you're just going to check whether there's a solution which is satisfying the implicit constraints, right? And for that, you essentially use a constructive version of the theorem of the alternatives. And if there's no such point, you can stop. And if there is such a point in a affine hull, you actually already know that there's a point in a polyhedron, which is in Ln. So the only thing you need to do is actually how to find it, right? And so you go back and think of what we did for the proof of the lemma. What you did is find a little ball which is defining your relative interior, right? So you need to find a ball, and we're going to pick the ball to be as large as possible. And I give that in my 250 class, how to find a ball of largest radius into a polyhedron. You can do that by writing a linear program for that. So that's what you do. And then you just use density again to just find something in the ball, but know which is in Ln, and that's the point that you were looking for. So of course, there are lots of details because you have to make sure that numbers don't get too big, right, and so on. But conceptually, that's all you do. You just implement that little lemma about affine hull versus points in the polyhedron. All right, so by now you might say, okay, the theme of my talk was to say, let's bridge integer programming with linear programming. You might be thinking, everything is collapsing to linear programming. This is boring, right? So let's just look at support sizes, right? So I'll look at a problem in standard equality form, right? So ax equal to b, x is non-negative, and my matrix A here has m rows and n columns. And we know that if it has an optimal solution, it has an optimal solution with support at most m, right? So what is the support? Well, I look at all the entries of my solution, and I would just count the ones which are non-zero, right? And I know this is to be true because if I have an optimal solution, I have an optimal basic solution. Okay, so do I have anything that looks like that for, say, dyadic programming? If I replace x being, add the additional condition that x is dyadic? No, it just completely breaks down. So here's an example. There's an infinite family of matrices. They each have just one row and an arbitrary number of columns. And I just look at the feasibility problem. I look at all the feasible solutions. So ax equal to 1, so 1 is just 1, because it's just a single constraint. X is required to be greater than or equal to 0, and I just added the condition that it is dyadic. So it has at least one solution, otherwise I'm cheating. And every single solution is going to have support n, right? So you can make example like that. So this is completely different from linear programming, right? Because here I have m equal to 1. For linear programming, the support would be 1. Here the support is n, right? So in particular, it tells you that you can't bound the support by a function of m only, right? You need something else. Well, those examples, there's a whole series of examples you can make that look like that. There's not just one. They all have a common property. Some of the entries become really, really large when you do that, right? And so you can have a bound on a support that takes into account the largest entry in your matrix A. So we're going to look at the infinity norm. And let me give you one such result, right? So same problem as before. And it says that the support is bounded by m times. So here you got a log of m here. And here you got a log of A infinity. So A infinity, I just look at the absolute value of the largest value in A. And now you get a bound on the support, right? So if A, for instance, is a 0, 1 matrix, then you get something of the order m log m, right? Okay, so not behaving like linear programs. All right, so this is my second part of the talk. I got 3 parts, so I think I'll be here all day. So one thing that people have liked to do historically is to look at linear program and say, what classes of linear program are going to guarantee that among all the optimal solution, I have an optimal solution that is integer. And so I'd like to extend that a little bit to by replacing integer with p-adic, right? So looking at linear program that have the property that I'm guaranteed to have an optimal solution where all the variables take p-adic values, right? So rational where the denominator is the power of p. So let's just review a little bit what is known about integer programming, right? So if I want to guarantee that for any choice of C, among all the optimal solution, I have an optimal solution that is integer, the way to do that is just to require that your polyhedron is integral. There should be an arrow that says 1 and 2 are the same, right? And what do we mean by an integral polyhedron? Well, we just mean that every minimal face contains an integer point, right? So if your minimal faces have dimension 0, it just says that every extreme point of the polyhedron is sitting on the integer lattice. Okay, so this is classical result. And so you could ask the same question, right? What are the requirements you need to ensure that for any choice of objective function, among all the optimal solution, one of the optimal solution is going to be p-adic, right? So all the variables take p-adic values. And this is equivalent to requiring that your polyhedron is p-adic. And what do we mean by p-adic? Well, we just mean that every minimal face contains a p-adic point, right? So that's a half integral polyhedron here. The red things are supposed to be the integer lattice. So in particular, it's dyadic. Now, this is not a really surprising result. And so by now, you might be thinking, oh, they're just going in sort of parallel lanes, right? Everything that you can do for integers, you can do for p-adics. But I'm actually going to show you that those two things actually merge. And here's one place where it starts merging a little bit. So suppose that I take a polyhedron and I tell you that it is both p-adic and q-adic, meaning that for every minimal face, you have a p-adic point, and for every minimal face, you have a q-adic point. Then, in fact, I claim that the polyhedron is integral. So if it's integral, it's p-adic for every choice of p, right? And there's a very simple proof that just relies on the theorem of the alternative. And let me not do that one. Let me just tell you why it's true when it's pointed. So when the minimal faces are a single point, right? So you look at every extreme point, it tells you that where all the entries for that extreme points, the denominators are powers of p, and the denominators are also powers of q, and p and q are different primes. So the denominator has to be 1, so it's integer, right? But that works even if it's not a pointed polyhedron. So I'll get back to that result a little later, and I want to talk a little bit about generalization of total dual integrality. All right, so this is a seminar and a review course. So I look at a primal and dual pairs of linear programs. P and D here. And we say that a system of inequality AX smaller than or equal to B, so those are the constraints that define the primal problem here, is totally dual integral if for every C which is integer, for which D has an optimal solution, it has an optimal solution that is integer. Right? That's what we called total dual integrality. And it has a number of nice properties, and one of the things that it imposes is that if you have a system that is totally dual integral, then it imposes that the polyhedron which is described by the system of inequality is going to be an integral polyhedron. Every minimal phase will have an integer point. So I'm going to generalize this notion of total dual integrality in the most straightforward way possible. Everywhere I have integer, I'm going to put p-adic. You could define it for a more general set L's, but we're just going to work with p-adics. All right, so same primal dual pair of linear programs. And then I'm going to say that my system is totally dual p-adic if for every choice of objective function for which D has an optimum, it has an optimum solution which is p-adic, meaning that every variable takes p-adic value. And what can I prove with this? Well, the same thing as before, which is if I have a system which is totally dual p-adic, and the right-hand side is integer, then my polyhedron is p-adic, meaning that every minimal phase contains a p-adic point. Again, it looks like total dual integrality is one lane, p-adic is another lane. So now let me merge the two lanes now. So total dual integrality is a way of proving that a polyhedron is integral. Let me give you a weaker sufficient condition to prove that a polyhedron is integral. You pick two primes, P and Q, right? B still has to be integer. And then if your system, AX smaller than or equal to B, is totally dual p-adic and totally dual q-adic, then your polyhedron is integral. And of course, if my system was TDI, it would be p-adic for every single p, right? So I'm just requiring it to be somehow p-adic for two distinct primes. And we proved it, right? Because if my system is totally dual p-adic, then the polyhedron is p-adic. Similarly, the polyhedron is also q-adic, and we said that if it was p-adic and q-adic, it's integral. Right. Now, why is this surprising? I find this result surprising. Because the way you prove that a system is p-adic is to use density, because you work with dense set. So you can prove that, in fact, we have characterization of p-adicness, which is just in terms of density. So you can potentially prove something about integrality of polytopes using notion of density. But the fact that a polyhedron is integral has nothing to do with density. It's just saying, here's a bunch of points which are sitting on the integer lattice. But it looks like you can use density to prove things about integral polyhedra. So I find this surprising. All right, so let me now move on to another part where I'll show that results about p-adic and q-adic sets give you something about integral sets, right? So let's go back to total dual integrality, right? So we have this result that if you have a system that is total dual integral and the right-hand side is integer, then the corresponding polyhedron is going to be integral. Now, so being integral for the polyhedron is a necessary condition, but it's not sufficient because, well, you can make a million examples. So here's one, right? This is a system of inequalities here. This is a corresponding polyhedron. It's integral. But this system is not TDI. And so maybe it's not surprising, right? Because it looked like they're somehow different objects, right? Being TDI is some kind of algebraic condition, right? I'm saying you have this infinite family of linear programs, and I want for all of them to have an integer solution. And then being integral is just a geometric object, right? But nonetheless, I think there should be a geometric characterization of total dual integrality, something that's purely geometric. And I can't give you one because I don't know what it is, but I'm going to give you one in a special case. And so I have to define another notion. So let me just say that a system of inequality is resilient. And I have two conditions here. So the first one is that you look at the corresponding polyhedron, and I want that to be integral. And then the second condition, it's going to look a little weird, so I'm going to make a picture afterwards. So what does this condition say? Well, it says take any one of the constraints here and take the right-hand side. I'm assuming that A and B are integer, I should say that. Take the right-hand side and just decrease it by 1. So essentially what you're doing is you take one of the constraints and you're just shifting it a little bit. Whenever I do that, I want to ensure that the polyhedron is still integral after doing that. Right? So it was integral, and I shifted any constraint by 1, the left-hand side, the right-hand side. It should still be integral. So let's just illustrate this on a little example here. Right? Here's a polyhedron here. It's integral, so I satisfy the first condition here. And if I replace, say, the 3 by 2, right? This constraint here just gets shifted like this. So my new polyhedron is this little triangle here, which is still integral. And you can try it with the other constraint. It will just shift this one here up, or this one here up by 1. In all cases, you're still left with an integral polyhedron. Here's an example of where that doesn't work. If I replace a 6 by a 5, right? This is going to be my new polyhedron there, and this is going to be an extreme point. It's not sitting on the lattice, so it's not resilient. So what does this have to do with total dual integrality? So we have to make a number of assumptions. The important assumption is that the polyhedron that we're looking at is non-degenerate. The other one is because I've been too lazy so far to try to make it more general. So it should also be pointed and full dimensional. But the important one is that it's non-degenerate. So it means that for every extreme point, because it's pointed, the number of constraints that are satisfied with equality is exactly equal to the dimension. Right? And under those conditions here, you have the following result, that being TDI is exactly the same thing as being resilient, right? Which again is surprising because TDI-ness is not a geometric condition, right? But being resilient is sort of geometric, right? It's integral, and you shift things a little bit, it still has to be integral. By the way, this was a surprise because we were not looking for this at all. We were just playing with this p-adic system and trying to understand them. And then there were a bunch of lemmas, and we were like, oh, what happens if we put all of those things together? And then that came out of it. Right. All right. So last topic I want to talk about is a conjecture of Paul Seymour that dates back from the mid-70s. In fact, this was a conjecture that really motivated a lot of the work that we were doing. And it's about dyadic solution in linear programs. And so here's a conjecture, now that we have all the language for it. So I pick A to be a 0-1 matrix, so all of the entries are either 0 or 1. And then look at the set covering problem here, AX greater than or equal to 1, X non-negative. And the conjecture says that if this system here is integral, then the corresponding system AX greater than or equal to 1, X greater than or equal to 0, it's totally dual dyadic. Right? So it means that when I write down the dual of the set covering problem, right, as long as the objective function C is integer, among all the optimal solution, I always have an optimal solution which is dyadic. Now it's a weird conjecture because why dyadic? Why not p-adic, for instance? Well, it's false if it's not 2, because there's an example where it's, you have 1/2 solution, so that doesn't leave much room, but it's still mysterious. So I didn't believe that conjecture at all, but it seems to be true for a lot of cases. And let me just mention some of the cases without getting into too many details. So the first 2 cases are sort of cheating, because sometimes we know that the system is 1/2 TDI, right? Meaning that the dual solution or half for the duals are always half integral, right? And so, of course, that will tell you that, in particular, it's dyadic, right? But the last 2 are really using density arguments. So for t-joint of graphs, it's true, and for dijoints in directed graphs. And I want to discuss in the last few minutes what this result is actually saying in concrete language. So switching gears to graph theory now. So I'm going to look at a directed graph. So every arc is oriented. And the first notion I need is the notion of a directed cut. So what's a directed cut? Well, it's a cut in the underlying graph, and it's directed, meaning that every arc is going from one side of the cut to the other side of the cut. That's a directed part that you have there. Okay, so this is the first object, directed cuts, right? So a subset of arcs that forms a cut where everything is going from one side to the other side of the graph. And then the other notion, which is important, is a notion of a directed join. So there are 2 ways of thinking about this. So one way of thinking about this is to say that you're looking at a set of arcs that intersect every directed cut. So let's just think of what that means. So if I have a set of arcs that intersects every directed cut, what happens when I contract all of those arcs? Well, if I have an arc which is in a cut and I contract the arc, I make the cut disappear. So if I have a set of arcs that intersects every directed cut and I contract all my arcs, I make all the directed cuts disappear. So what am I left? I'm left with a graph which is strongly connected because there's no directed cut. So you can think of a directed join, or dijoin for short, as just being a set of arcs that have the property that after contraction, your graph is strongly connected. Okay, so you have those 2 objects, directed cut, all the cuts going from one side to the other, and directed join, set of arcs whose contraction makes your graph strongly connected. And you have the following beautiful theorem that you're obliged to know, being in Waterloo, that says that the size of the smallest dijoin, right, so the cardinality of the smallest dijoin, is equal to the maximum number of pairwise disjoint dicuts, right? So collection of dicuts, no 2 of which share an arc. That's a beautiful theorem. And when you look at this beautiful theorem here, it has dijoin on top and it has dicut afterwards. So you say, let's just be clever and let's see what happens if I swap dijoins for dicut. Just changing just a few number of characters here. How bad could it go? And then you get a conjecture, which is known as Waterloo's conjecture. It's been open for many, many years. And it says that the size of the smallest dicut should be equal to the maximum number of pairwise disjoint dijoints. So let me just illustrate the conjecture here on the example. So this is another counterexample to Waterloo's conjecture. So I should be able to do this. So the size of the smallest directed cut is 3. Right? I take this directed cut here, those 3 arcs here. That's a directed cut. It has 3 arcs there. Can't find a directed cut with 2. Right? And then if I look at the red arc there, if you contract the red arcs, this is going to form a directed cycle. This is going to form a directed cycle, and so on. So it'll be strongly connected. Similarly, if you contract the blue arcs, your graph becomes strongly connected. And if you contract the green arcs, your graph will become strongly connected. Right? So this is a collection of pairwise disjoint dijoints. So what Waterloo says is that you should always be able to do that. Now this conjecture seems really, really hard So let me give you a dyadic relaxation of that conjecture. And it's a really, really big relaxation. All right, so what am I doing here? I'm picking k. I don't get to, I have to pick the appropriate k for the appropriate digraph. I don't get to choose it, right? And then what I do is I take every arc and then replace it with 2 to the k parallel arcs, right? So I do something like this. If you give me k equal to 2, right, then every time I have an arc there, I just replace it with 2 to the 2 arc there, right? So I get a much bigger graph, right? But once I do that, then Woodall's conjecture hold, right? The same kind of min-max thing. The size of the smallest directed cut is equal to the maximum number of pairwise disjoint dijoints. So this is just a way of saying that you get a dyadic solution to the dual, right? Because I'm just sort of scaling the objective function by replacing this arc there by this collection of arcs there. Now, how do you prove this? It's using density arguments, right? So essentially, it goes back to that lemma about you have a point which is p-adic, which is in your fine hull of a polyhedron. Then you get a p-adic point, which is in a polyhedron. That's essentially what we're doing here. All right, and that's the end of my talk. Thank you.
Okay, thank you for the great talk. I will hold, are there any questions? If there are, I will give you the mic to be recorded. Okay.
So I'm not familiar with this concept of density. It's new to me. So my question is that if we have a polyhedra, then we know that the convex hull of integer points of it is indeed a polyhedra, right?
Sorry, let's say that again.
If we have a polyhedra, then the convex hull of integer points of it is still a polyhedra, right?
Sure, yeah.
But it is not true for dyadic points in this polyhedra, right?
No, I don't think it doesn't need to, no. I mean, so, once you take the convex hull of an infinite number of points, all bets are off.
Yeah. So I was thinking that is it somehow relies on the fact that their integer numbers are not dense, but like the dyadic numbers are dense? Is it?
Yeah. So I think the reason this behaves differently from integer programming is exactly because of density, right? Mm-hmm. So this is what helps us work. The thing which is a little surprising is that there are, for instance, results about size of support. And when I first looked at size of supports for integer programs, right, I was thinking, well, this is because we were working with discrete sets. That's why it has large support. Mm. But it turns out that, no, that's actually not the reason, because the bounds you get for dyadic programming in terms of support looks a lot like the bound you get for integer program. So sometimes, I think one of the interests of doing this research is to sort of untangle, when you have a gap between what happens for linear programming and integer programming, where does it come from? And sometimes it comes from the discreteness, and sometimes it doesn't.
So is it the case that if I replace the integer numbers with another set that is not dense, we can state that like the convex hull of these points is a polyhedra? Can we conclude?
You're gonna, yeah. But as I mentioned at the start, right? So if you don't have density, then the class of problem that you're looking at is essentially back to integer programming.
Yes. Mm-hmm.
And so you have no choice. If you want to go outside the integer programming world, you're gonna be working with dense set. Mm-hmm. And then once you do that, then things behave differently.
Yes. Thank you.
Other questions? Okay.
Thank you. So, like, at some point you were like talking about that we can, if we show that a program is like p-adic, has p-adic solution and a q-adic solution, then we have integer solution. Yeah. So conceptually, like that's okay. But is there any place that actually this has been used to get an integer solution that hasn't been like directly proven?
No, I think this is a a theorem in search of an application. So if anybody has a nice application for it, yes.
Okay, yeah, thank you.
Has a question?
We didn't notice this a long time ago, so, you know.
So in your resilient theorem, you had this condition that the polyhedra should be non-degenerate.
Yeah.
Does that mean that the dual solution is unique?
The dual solution is unique, right?
So isn't that turning that into an algebraic condition? I mean, you're promoting it as a geometric versus algebraic.
Yeah, I mean, this is a little bit what happened. So what you can show is that this resilient condition, what it does is that it imposes that it's somehow p-adic for every choice of p. But when it's non-degenerate, you have solutions which are p-adic for every choice of p, but essentially the dual solutions are unique. So they end up being integer.
Mm-hmm.
So, yeah.
Yeah. Okay.
Any other questions?
So in terms of applications of your like Q-adic theorem implying TDI, what about taking theorems that are known and see if the proof's simplified? Like, do you get a simpler proof of TDI-ness for matching things, for example, by looking at
Yeah, I mean,
it's dyadic or triadic?
I think one should definitely try to use it, even in existing problems. We just haven't had a chance to because it's not an old result.
Okay, thanks.
Further questions? Okay, then I guess we can take questions offline. And thank you again.